if I look at any non-trivial subsheaf of E in this category, then a slope of f is smaller than or equal than a slope of E. Okay, so for instance, any new semi-stable sheaves must be torsion-free because I put the slope to be equal to infinity as soon as chain 0 is equal to 0. Okay, so this is the classical notion of stability that we have, and then it's easy to see that for any object there exists a finite filtration to semi-stable objects, which is called Harder-Narisman filtration. We usually denote it just by HN filtration. It just says that for any object E in this category, for any sheaf E, there exists a finite filtration like this. So it's a finite filtration such that I know that each of these factors, EI over EI minus 1, is mu H semi-stable, and a slope decreases. A slope of E1 over E0 is bigger than a slope of E2 over E1, and so on. So this is what we have classically for slope stability. But when we want to study the variety X via this information, the only way that that we can vary this data is just by varying the polarization that I choose from the beginning, that which just goes to GIT, that Josh will explain it in full details in the lectures. But the other viewpoint is that, okay, so let's just look at other abelian categories which catches the information of the geometry of X. Okay, so instead of just working on this abelian category of coherent sheaves, we can just look at some other abelian category which gives us maybe some more data of geometry of X that we can use. And that's basically the whole, the starting point of Bridgeland stability conditions. The way that we find this other abelian category is via the bounded drive category of coherent sheaves on X. That's why I briefly explained this notion. So it's just, just very briefly I can explain what is this category, which is just noted by the bounded drive category of coherent sheaves on X. Okay. So the objects in this category are just complexes of coherent sheaves. So we have notion of complexes, which is just the sequence of coherent sheaves on X. Sequence like this one. So we are saying it's a complex when the composition of two consecutive ones is just 0. Okay, so di over di minus 1 is 0 for any I. Okay, and it's just called bounded complex. When there are only finitely many non-zero coherent sheaves on this sequence. So when the i's are 0, when I is very large, and I is very small. Okay. So let me just also recall you the notion of cohomology. Because of these assumptions that the composition of two consecutive maps are 0, we know that the image of di minus 1 is inside of kernel of di. That's why I can define hi of this complex a dot, or maybe e dot, to just be kernel of di over image of di minus 1. Okay? That's basically the whole information that we care about it when we go to this bounded drive category of coherent sheaves. That's why we define the notion of quasi-isomorphism between two complexes. Just check the notations. Or maybe before going to the notion of that one, let me just first introduce the notion of category of complexes. So just via that complexes, we can, as soon as I start, before, maybe I can, whole of the setup that I have here is not just for this abelian category of cohesives. It can be just any abelian category. So to make it more general, although in my talk I only need that abelian category, but anything can be explained for any abelian category. So I fix an abelian category A, and then we can define the notion of complexes, bounded complexes, and cohomology. Okay? Then the notion of category of complexes that I'm going to denote by com B of A is an abelian category whose objects are just, as I said, bounded complexes over A. And the morphisms are just homomorphism of complexes. Morphisms are just homomorphism of complexes. Okay. So up to now, there isn't any hard things to do. It's just I'm replacing this original abelian category A by this abelian category of com B of A. But the whole problem is that I am not really interested in the objects in the complex itself. I'm interested in the cohomologies. That's why I have to modify these morphisms. When two complexes have the same cohomology, I want to just assume that they are the same objects. That's why we define the notion of quasi-isomorphism. So a morphism in this category of complexes over A is called a quasi-isomorphism. Is a quasi-isomorphism if the induced map on cohomology on this HI of A, this or maybe let me just write it as on cohomologies, is an isomorphism on cohomology. So just like HI of A to HI of B for two different complexes A and B is an isomorphism. Okay. So then we can define finally the notion of this bounded derived category of A as just localization of this category of complexes by these quasi-isomorphisms. Okay. So let me just write it as a theorem. So that I don't want to go to the full details of that notion, but this theorem uniquely describes what is this bounded derived category of A. Okay, so it just says that there is a category that we denoted by dv of A together with a functor Q from this category of complexes to dBA such that three properties are satisfied. The first one is that I want that this Q identifies objects in these two categories. So in other words, any object in this bounded derived category of A is still a complex of objects in A. So the first condition is that Q identifies objects in this cone B of A and DBA. The second thing is that I want that if I start with a quasi-isomorphism in this category of complexes, it just sends it to an isomorphism. This is just the things that I told you, that we only care about cohomologies of a complex, not each of the object itself. So if F is a quasi-isomorphism in cone B of A, then Q of F is an iso. Okay, and finally we want that this category DBA to be minimal with respect to these two conditions, which categorically just means that if I look at any functor F from cone B of A to a category D, which satisfies these two conditions, I and 2, then it uniquely factors via this function. Okay, so is there any question for the definition? Okay, great. So, via that definition, since the objects are still complexes of objects in A, you can define the notion of a functor from DBA to itself, which is just a shift functor. So it's just shift by 1 from the category, from this DBA to DBA itself. It just, if I start with a complex E dot, E dot shifted by 1 at degree I is equal to E at degree I plus 1. So basically, I just change the grading of any complex, and then composition is just shift by n. Okay, so this is the only functor that I'm going to use. But the whole point is that although the original category A that I've started with that and this category of complexes, cone B of A, are both abelian categories, the category that we construct via this way, this DB of A, is not an abelian category. So the point is that DB A of A is not a priori an abelian category in general. And that was exactly the point that Verdier and Grothendieck tries to understand what is the structure of this new category, and they came up with the notion of triangulated category. But it is a triangulated category. Okay, so fortunately, we do not have that much time that I go to the details of what are triangulated categories. Just, the key point is that in an abelian category, I have the notion of kernel and co-kernel. So I have the notion of short exact sequences. But in triangulated category, I'm replacing short exact sequences by a collection of exact triangles. So here we have a collection of exact triangles, which behaves more or less like short exact sequences. It's still a collection of 3 objects, E1, E2, E3, which satisfies some assumption when we look at the morphism between them. And as I said, it just behaves like short exact sequences in an abelian category. Okay? But we will see some examples during the talks. What are these short exact sequences? For instance, if I look at any short exact sequence on A, then it will be an exact triangle in DB of A. Okay. So, if there is no question, I want to go to the notion of Bridgeland stability condition. So we are this data which is just defined on this triangulated category. We want to define the notion of Bridgeland stability conditions, but the main idea, the original idea of Bridgeland stability condition was defined on any arbitrary triangulated category. But since I want to have a more geometric tags, and it's just two tags, I only concentrate on the bounded derived category of coherent sheaves on X. Okay, so I'm going to define to only concentrate on this triangulated category from now on. Before going to the notion of Bridgeland stability, I only need to say one final thing, which is Grothendieck group of an abelian category. Grothendieck group of this category of coherent sheaves or any abelian category is just a free abelian group generated by this object. Let me just write it down. It is the free abelian group generated by objects in coh of X, subject to just one relation, abelian group of generated by isomorphism classes, of course. Isomorphism classes of objects in coh of X, subject to the relation that if I have a short exact sequence of coherent sheaves like this, then I identifies the class of E prime by E plus E double prime. Okay, that's the only relation that I consider to define the Grothendieck group of X. Okay.
Sorry.
So better. Okay. So, and let me just maybe write in other words. But I need a finite dimensional lattice. That's why in practice I cannot really work with the Grothendieck group. I need to fix a finite dimensional lattice called lambda. So from now on, I'm fixing a finite dimensional lattice lambda and a surjective morphism. And a surjective homomorphism V from Grothendieck group of coherent sheaves on X to this lattice. Okay, so that's the starting of this theory of Bridgeland stability. I need to fix this lattice lambda and this surjective morphism V. Okay, and work with this lattice from now on. Okay. But in the examples that I will explain probably in the next talk, this lattice is just a numerical Grothendieck group. But I will explain it later. Okay. So now finally we can go to the notion of Bridgeland stability. So a Bridgeland stability condition sigma is just a pair A and Z, such that, okay, so let me just Bridgeland stability conditions on dB of these coherent sheaves of X. Okay, so I want to concentrate only on this triangulated category from now on. Is it just a pair A and Z, where A is just an abelian subcategory of dB of coherent sheaf on X. this is just the first thing that I promised when I started. I want to choose abelian subcategories inside these triangulated categories, which could be a priori different from coherent sheaves of X. Okay, so A psi dB co of X. Let me just denote it by dBx from now on. Is an abelian subcategory. But I want a bit more than just being an abelian. I want to get sure that I can obtain any object in this triangulated category via extension of objects in this A. That's why we need to assume that A is actually part of a bounded T structure on this triangulated category. But I don't want to go to that details, because we don't really need it. But to be just precise about the definition, I just write it here that A must be part of a bounded T structure. And Z here is just a group homomorphisms. Let me go to the other part. And Z is a group homomorphism from ascending group of X that I've just defined there to a complex number. It's just a group homomorphism, but I also want that this function Z factors via the surjective map that I've explained there. So I want that this map just factors via the lattice that I've defined to just be sure that we only care about a kind of finite dimensional lattice in the end. So it's important to for later on for the topology of this space. It's important that we fix a finite dimensional lattice instead of working on a infinitely long. And so I want a group homomorphism, which physically is just called central charge or a stability function. Central charge. Yeah, maybe I should say in the beginning that the notion of Bridgeland stability condition is completely motivated from pi stability in physics. So it's just basically a mathematical interpretation of what they have in physics, in this language. So I want that this choice. So I had two choices: this choice of abelian subcategory and this choice of central charge Z to be compatible to each other. So I want that they satisfy several conditions. The first condition that I want is that, as I said, I want to generalize the notion of mu-H stability. Okay, so I've had that abelian category, and I want that this function Z gives us an ordering for the objects in A. So this ordering can be defined if I just restrict this function Z to, for instance, have phase in the upper half plane. So I want that for any non-trivial object in this abelian category A, Z of E can be written as RE exponential of I pi phi of E, where R of E is positive and phi of E is just phase of E is between 0 and 1. In other words, if I look at the image of this central charge, the image is in the upper half plane or negative real line. Okay, so this is just Z of E. Okay, so for any object, I have a well-defined notion of phase, which, as I said, varies from 0 to 1. Okay, now using this ordering, we can define a stability of that object. So, I'm inside. I'm still inside the conditions, but I have to define the stability here. Just as we had for mu-H stability, we can say that an object E in this abelian category is, let me just call it sigma semi-stable, where sigma is just that pair, A and Z, is sigma semi-stable if I look at all non-trivial subobjects of E in this abelian category A, then phase of F is a smaller or smaller than or equal in case of semi-stability than phase of E. This is exactly what we had for mu-H stability. Okay? Now we have the notion of sigma stability, and the second condition is that exactly like mu-H stability, we want the notion of Harder-Eisman filtration. So the second condition is filtration to semi-stable objects. Yeah?
Yeah, it's a question online, yeah.
Okay. Okay, go ahead. Yes, we are hearing you. What do you... Sorry, say it again. So, maybe complete your sentence. So you said that you fix an object in the abelian category A, and then what? Okay. Is a set? No, it's just a priori is just a complex of coherent sheaves. Set means what? What set means? Set. It's just an object in the category. Okay, yeah, it's just an object in the abelian category.
To be a set theoretic question, like is the set of all objects really a set? How logically
Yeah, of course, yeah. So is it that question? Yeah. So yeah. Okay. So probably we can discuss that one later. Yeah, but yeah, maybe I didn't get your question. Okay. So, but maybe we can discuss it after the talk. So I was. So, as I said, we want that this pair of A and Z, via that notion of semi-stability, satisfy Harder-Eisman property. It just says that if I have any non-trivial object in this abelian category A, then there exists a finite filtration to semi-stable objects. This is just exactly what we had for mu H stability. So it's a filtration so that each of these factors, EI over EI minus 1, is sigma semi-stable, which I just defined what I mean by sigma stability. And I want that the phases just decreases. So phase of E1 over E0 is bigger than phase of E2 over E1, and so on. Okay. And
Sorry.
go ahead.
So the condition in one is, I mean, you're just defining what sigma semi-stability means. So is this the condition you impose on A?
No, it's not a condition. No, it's just.
Because you're saying this map such that one.
Yeah, I said that I have to put a definition in the middle. If you have any abelian category via that property that the image of this central shard is in the upper half line, we can automatically define phase. And I want to just say what that word means, basically.
But the condition is the phase being between 0 and...
Exactly.
Yeah, that's the condition. Yeah, I said, yeah. So here is the condition that we want. Yeah. But as soon as we have that condition, this definition is automatic. Yeah. Okay. So we usually just write it as the maximum phase in the filtration, phase of E to be phi plus of E, and the minimum phase in the filtration just defined to be phi minus of E. Okay, so it's just the notations that we use. And the third property is support property, which is the final property that we need for the notion of Bridgeland stability. But I'm not going to the details of that because it's not essential for today's talk. The idea is just as we have for mu H stability, the classical Bogomolov inequality, a kind of quadratic inequality that a stable object satisfies. Here we want the same things, a kind of quadratic inequality that all of sigma semi-stable objects in my abelian category satisfy. Okay, so, but via that definition, I can change this abelian category A and the central charge Z to obtain different stability conditions on my category. And that's why I gain a set of all space, stability conditions. So I denote it by a stab of dBx to just be the set of all Bridgeland stability conditions. Okay, so which means that set of all pairs A and Z which satisfies these three properties. Okay, but the cool point is that you can construct a natural topology on this space, which is just maybe just write it down here. So this can be given a natural topology. A natural topology, which is just the coarse topology which satisfies this condition. So in this notation we have to be very careful. I fix the lattice lambda and the function b. So in the whole of the definition, I'm fixing that. So, but in the notation, you can put these two conditions that I'm looking at that set of Bridgeland stability conditions. Okay. So then the topology can be just given as the coarse topology. Such that if I pick any object in the bounded derived category of X, then three maps are continuous. Then maps, so I can, for any fixed object, I can consider map that sends any pair Z to the central charge. Map sends A and Z to the maximum phase in the filtration. of E, the ones that I've just defined, the hardenized configuration, and the one that sends this A and Z to the minimum phase. I want that all these three maps to be continuous. And via that, we can define the natural topology on the space of stability conditions. And then the key theorem in Tom Bridgeland paper is that via that topology, actually, the space of a stability condition is a complex manifold. So this is theorem due to Bridgeland himself, just says that the map Z, which sends, goes from a step of this dBx to group homomorphism from this lambda that I fixed to a complex number. Okay, so I can only concentrate on the central charge. So it just sends a pair A and Z to the central charge Z. Okay. Then the claim of the theorem is that this map is actually a local homomorphism. Is a local homeomorphism. And so step of dBx is a complex manifold. Yeah, it's a very deep result because it just says that basically locally, when I vary the central charge Z, there exists a unique way to define this abelian category A so that we have a Bridgeland stability. So it's a very non-trivial result. Okay.
Sorry to be fussy, but
Sorry, say it again.
you also need the transition functions to be holomorphic, right?
Yes, yeah. Yes, yeah, exactly, yeah. Okay, so it's a complex manifold of rank of this lattice lambda that I originally fixed. Okay, so the final thing that I want to say about this general notion of Bridgeland stability is wall and chamber decomposition. I wish to take that one, I did not. Josh probably explained that notion in the GIT setting, but it's just more or less similar idea. So the point is that now I have a complex manifold, this stub of dBx, and the question is that if I fix an object E in this triangulated category, then how the notion of stability of this object changes. So if I start with a stability conditions Z, A, and Z, where my object is stable, then when I slightly deform this stability condition via that topology, does it remain stable or not? The question is exactly the stability. Strict stability is an open property. That's why we have the notion of chamber decomposition. So let me explain a bit more details. What is that? So as I said, this is just the simplest way to explain this wall and chamber decomposition, but the idea is a bit more involved. Okay, but the idea is just you can catch what is the picture behind it. So I'm fixing an object in this drive category dx. Then the claim is that there is a collection of walls. That I'm denoting by WI for I in this index I, such that several conditions are satisfied. The first the first thing that I want is that each of these Wi is a closed submanifold of a staff of X. Wi is a closed submanifold of staff of X of real codimension 1. Okay, and this collection is locally finite, so the collection of walls are locally finite, which means that if I look at any compact subset of a stab of X, it intersects only finitely many of these walls. It's too high for me, I cannot bring it down. And I want that my object E, my fixed object E, to be semi-stable, strictly semi-stable for any stability condition along my wall. So the third condition is that my fixed object E is sigma semi-stable, strictly semi-stable, and just emphasize on that, strictly semi-stable for any stability condition sigma which lies on a wall Wi for all I in this index I. And the final property is that how is the complement of these Wi's. Okay? It just says that if I look at a connected component, C inside this stab of dBx is a connected component of the complement of these walls. This, if I look at the union of all these Wi's and look at this complement and then look at a connected component of that and pick two stability conditions, we need to pick two stability conditions on this C, then my fixed object is sigma 1 semi-stable if and only if E is sigma 2 semi-stable. Okay. So if, for instance, if we look at a real two-dimensional slice of a space of a stability condition, so it just looks like this. So the walls are just some lines like that ones. And the claim is that if I look at any chamber here, then a stability of my object is not changing when I'm varying the notion of a stability here. This is just a two-dimensional slice of that. But my object E is strictly semi-stable along the walls, so it switches from stability to instability or vice versa whenever I'm crossing one of these walls. Okay. So that's the whole thing that I want to just say about the general notion of Bridgeland stability. Is there any question before I go to examples?
What do you mean by strictly semi-stable?
No, that's a very good question. So, strictly semi-stable means that it cannot be stable. So, I said that it's strictly stable when the face of all sub-object is strictly smaller. When I'm saying it's strictly semi-stable, it means that there is definitely an object with a sub-object with the same face. Yeah.
Is
Yes.
there any hypothesis about how the walls meet
heat? Are they pairwise transverse, for example?
Yeah, there are lots of things that we can say about the intersection point. I'll explain them on the case of surfaces, how they behave in the examples.
So these walls are uniquely determined
Yep.
by the property that is in stable, semi-stable dumps.
Exactly. Yeah. So it's just exactly the points that you deform this this pair of stability conditions. Now, as soon as it switches to a different types, from stability to instability or vice versa, it's exactly the location of faults. Yeah. So it's just basically all of the stability conditions. I'll explain one of the examples, so you will see how we define them in examples, reality. Any other question?
Is it possible to say what the image of this map is to the H to the home of numbers?
Yes, in examples, yes, or prior, yeah. So for K3 surfaces, it's completely explained by Bridgeland and Bayer. Yeah. Okay, so let's go to examples. So the first example is the one that I start with that, which is just mu H stability. Okay, so which is dimension 1. So let's assume that dimension of X is equal to 1. So this is the first example of Bridgeland stability that we can construct, basically. So before going to the example, let me just explain what is the lattice that I'm going to fix from now on. It's just the numerical Grothendieck group. So maybe before going to that, let me just quickly say what is that. So the lattice that I want to fix from now on is the numerical Grothendieck group X over X, which is just the quotient of the Grothendieck group of X that I've just defined, over T, which is just the null space of the Euler form. It's just chi of an F. Sorry, it's just I'm very. Okay, that's the Euler form.
This up again?
Say it again.
Would you leave the blackboard up?
Sure, sorry. Other one.
I think this one, because you can't see from...
Oh, that's the only problem. Okay, maybe I don't use that one then.
Do you want me to switch these two boards?
Yeah, it would. You're sorry.
I will try. I don't know. I mean, I'm perhaps not much taller than you.
Okay, great. Thank you. Okay, thank you. So this is the lattice that I'm going to fix from now on and use it. But if you are not familiar with this numerical Grothendieck group, it's just the image of the chain character map to cohomology. So let me just maybe write down. It's just the image of chain character map from the Grothendieck group of X to cohomology. So just star of XQ. Okay. So the image is, this is a function V basically that I've chosen, and the image is this numerical Grothendieck group inside H star of XQ. Okay, so the function V that I've said in the beginning is just chain character, and the lattice is numerical Grothendieck group. Okay, so let me just use the other words for the case of our example. So when you are on a curve, you have only chain 0, chain 1, just degree and rank. So there are not too many options. So let me just explain the first ones, which is just the classical stability that we have. So in the curve case, when X is just a curve, I can define, so I need to choose a pair, yeah? The pair that I choose is that an abelian category A, just the coherent sheaves on my curve C. So X is just the curve C. And I need to fix what is that central charge. As I said, I want to go from the numerical growth in the group of C to complex number. So I need to just say what is the image of any object here via the rank and degree. So if I look at this function, for instance, then let's check together that does it really works or not. So the first thing that we want that the image of any object in my abelian category to be in the upper half plane or negative real line. Okay, so I know that any coherent sheaf has a non-negative rank. Okay, so the rank, if the rank is positive, it's all fine. But if the rank is 0, then I know that the degree is positive. So the image would be on the negative real line. So it just satisfies the positivity property that I wanted. So, and then, so this is just the image Z of E. And how is the phase? Phase for any object is just minus real over imaginary part, basically the ordering of the phase. So ordering is the same as minus real part of the central charge over imaginary of that central charge, which is, here is just degree over rank, which is just the classical stability that we have for a coherent sheaf E. Okay, that's why you can easily see that a coherent sheaf E is, via that choice of sigma, is sigma semi-stable if and only if it is a slope semi-stable. Okay, so it's exactly the same notion. But the bad news is that these are all, as soon as the genius of the curve C is bigger than 1, these are up to a GL2 action, which I'm not going to the details of that one. This is the only stability condition that we can construct on the bounded drive category of coherent sheaves on a curve. Okay, so it's just not adding anything to our old knowledge of classical stability. But as soon as we go to higher dimension, the theory is much more involved. So, but to just, I have few, so just as an exercise, let me just tell you what is happening. So the first hope is that when I go to higher dimension, the same category of coherent sheaves might work. So for instance, when I go to dimension of the surface case, the question is that is there any stability condition Z so is there any Bridgeland stability condition sigma A and Z on this dB of X when dimension of X is bigger than 2, bigger than or equal to 2, such that A is a category of coherent sheaf on X. And unfortunately, the answer is no. We cannot construct any stability condition so that the positivity property is satisfied. It's a very easy exercise that you do, because the first problem is the positivity property that I want here for the objects in the category of coherent sheaves. So, for instance, when the dimension of X is equal to 2, the imaginary part of my function is just a linear map of A churn 0, B churn 1. For instance, when Picard rank is 1, it's easier to see, and C churn 2. But I want that this imaginary part to be non-negative for any coherent sheaf on X, and can easily see that. And the other condition is that if this imaginary part is 0, then the real part must be negative. So these two conditions cannot be satisfied together for any linear maps of churn 0, churn 1, and churn 2. That's why we have to go to other choices of this abelian subcategory of DBX. And that's exactly the point that the whole beauty of theory of Bridgeland stability conditions starts. Okay, thank you. Thanks so much.
Let's go straight to the question then.
So in dimension 1, you said that with hard coherent sheaves, there's only one.
Up to GL2 action, up to an action of a group. So basically, this action does not change the stability of objects. It just changes, the central charge in a formal way. But a stability of an object is not changing via that action of GL2.
So that doesn't change the hard?
It changes hard via a tilt, but a stability of objects is not changing.
So there's only one stability condition
after this GL action.
So when we talk about the wall and chamber structure, the E that you have in condition 4, that's the same E as the object that you've chosen in the beginning, right?
So E is fixed. No, E is fixed.
Okay, E is fixed.
So in whole of the construction, I'm talking about a fixed E.
So how can I imagine, or can you say something about how this varies as you vary E?
You will see in the next talk.
Is it GL2 action?
Yeah, GL2 plus R. It's just a universal cover of GL2R. Yeah.
Are there more questions? Yes.
So you started the talk with this situation where you had a variety, I guess, and then a line bundle H, if I remember correctly, and then you define the stability. So will you be able to recover this stability from some Bridgeland stability condition?
So this is exactly that one. For care, you don't have any choice. But when you go to higher dimension, it's not a Bridgeland stability, and the problem is, you can have the same function. Instead of degree here, you have minus churn 1 dot h to power of n minus 1 plus I churn 0. This is the only choice that you can have to have the same ordering. But the problem is that there are points that the image of the central char is 0. So the points, for instance, on curve is just a scraper shift. Any point supported in codimension 2. The image when churn 0 and churn 1 are 0, it's just 0. That's why it doesn't match with the original definition. And so what is called weak stability condition in this scenario.
You gave away the answer to the exercise. Someone.
Yeah.
Okay. Are there any other questions? Then I think we thank Soheyla again.
Thank you.